Okay, this will be Chapter 5, Lesson 4, and what we'll talk about here is something called Hess's Law. And the idea here is that we can calculate the delta H for a reaction from the delta H values of other reactions. And the reason this can happen is because chemicals are actually linked in the sense of we can look at their bonds and the breaking and the making of bonds. All that is linked together for a big picture. What this means for us is we can use a small number of experimental measurements to calculate the heat of reaction for a vast number of different reactions. This is actually a very powerful tool for us to determine the delta H's of many reactions. Here's a kind of an explanation of it. If we have two reactants, this is methane gas combusting with oxygen. Usually any standard combustion reaction produces CO2 and H2O. And that heat change would be negative 890 kilojoules. We can perform the same reaction in two steps. We can first form a bunch of CO and water and oxygen. That will take negative 607 kilojoules, and then we can go ahead and react that to produce our final products. That will take negative 283 kilojoules. And the point is, we can go this way and give us negative 890. We can go this way, and the total will still be negative 890. So Hess's law will allow us to do this. So we're going to do a quick little example, and then we'll do another one to solidify this concept. So we have two reactions here. The first is on the top here along with its delta H. The second one here along with its delta H. We're going to be able to use these two delta H's to produce the delta H of this third reaction, the heat of combustion of carbon to carbon monoxide. And I'll do this on the next page, and we'll kind of follow along, and then we'll explain the concepts behind it. So what I'll do is I'll actually rewrite the reaction that we are heading toward the one that we want to end up with. I'll write at the bottom, and that is carbon. And I will leave the state symbols off for clarity. Carbon plus half of an oxygen, producing carbon monoxide. And we're going for the delta H of this reaction. That's the whole idea. We want to determine the delta H. We will do that from these two reactions. The first one, carbon plus O2, giving us carbon dioxide. The delta H of this process will be negative 393.5 kilojoules. The second reaction will be carbon monoxide plus half of an oxygen, producing CO2. And the delta H of this process is negative 283.0 kilojoules. Now the idea here is this. We want to end up with carbon on the left side. Carbon comes from this first equation, and it is already on the left side, so we'll leave that alone. Carbon monoxide we want to end up with on the right side. That comes from our second equation, and it is actually on the left side. So in order to put it on the right side, what we'll have to do is we'll have to actually flip the equation. So what I will do is I'll draw a little arrow, and you can write flip on it there. So I will write the products where the reactants were, and the reactants where the products were. So I'll rewrite this equation as CO2 producing CO plus half of an oxygen. Now anytime we flip an equation around, its delta H actually becomes positive, or the sign of the delta H changes here. So this will actually become now positive 283.0 kilojoules. So we've flipped the equation, so I'll go ahead and cross the equation out. And now what you'll see is that everything works out, everything cancels out to give us our final equation. So our carbon is on the left side, our carbon monoxide is on the right side, and what we have is we have half of an oxygen on the left side. Looks like we've got ourselves the way to see this happen is actually the CO2 on the right side cancels out with the CO2 on the left side. So these being on opposite sides will cancel out, and the opposite sides of the arrows, if you take a look, they are actually, this one's on the right side of the arrow, this one's on the left side of the arrow. They will cancel out. Our oxygens, we have half an oxygen here, and we have a whole oxygen here. Remember, there's a 1, an invisible 1 there. So this half oxygen will cancel out with this half and leaving us half of an oxygen on the left side, and that's exactly what we want to have in our final product. So you can actually see that we are left with these three substances. If we've arranged everything correct to give us the final equation, what's left there to do is actually to total up our delta H's. So in this case, we'll actually take 283.0 kilojoules and essentially subtract that from 293.5 kilojoules. So go and do that on your calculator. And that should give us a total value of negative 110.5. And that essentially will be the delta H of this final reaction, negative 110.5 kilojoules. And that's what we're able to determine. So notice we're able to determine the delta H of a third reaction from the delta H's of previous reactions by rearranging them and canceling things out that appear on both sides. This is Hess's law. We're going to explain a little bit of what we can do. So what we can do is we can multiply a reaction by a whole number, as long as we remember to also multiply the delta H by that same number. We can reverse a reaction. We've seen this before. If we also reverse the sign of delta H. We can add reactions, so to making sure to cancel out anything that appears on opposite sides, on both sides of the chemical equation, and adding up anything that appears on the same side. And that's what we've done. And where this comes from is you've actually done this in algebra with something called systems of equations. They actually taught you the method that we are employing here for chemical reactions. That's why this works. So let's go ahead and do another example of essentially the same thing, a little more complex with a little more to go. So here we have, we want to calculate the delta H of this reaction using these three reactions. So we'll actually use the same method as we've just used, and we will try to do that here. So I'll go ahead and write again the final reaction toward the bottom. In the final reaction, we want to have 2 carbon reacting with H2, producing C2H2. This is actually something called acetylene gas. Let's make that carbon a little more visually pleasant. There it is. And again, we want to determine the delta H of this reaction. Here's what we're going for. The 3 reactions that are known, I'll go and write up here. C2H2 plus 5 halves O2. And now don't be alarmed by that 5 halves. It is actually not only legal and fun, but also very helpful oftentimes to use fractions in the balanced equation. And you'll especially see that in this chapter. So the delta H of this process is given to us negative 1299.6 kJ. The second reaction, we have carbon reacting with O2. And actually what I'll do is I'll leave, I think this will help out, I'm going to leave a little bit of space between them in case we have to rearrange something. So I'll go ahead and do this. We get carbon plus O2 giving us CO2. And the delta H of this process is given to us as negative 393.5 kilojoules. Our third reaction then gives us H2 plus half of an oxygen giving water, and the delta H of this process is negative 285.8. So effectively we've rewritten the reactions. That way we can now manipulate them. And here's what we need. We need 2 carbons on the left side of our final equation. Looks like carbon is already on the left side and it comes from this second reaction. However, we will need to multiply that by 2. So what I'll do is show that we'll have to multiply this whole reaction by 2. And then we can actually show that rewritten down here. So we'll now have 2 carbons plus 2 oxygens, providing us 2 carbon dioxides. Recall then, if we multiply the reaction by 2, we must also multiply the delta H by 2. So that looks kind of like a 3. Why don't we make it a 2? And so if you multiply this value by 2, if we do negative 393.5 times 2, we get ourselves negative 787. So the new delta H is negative 787 kilojoules. What you can do then is cross out the reaction that we flipped. Now it looks like we need C2H2 on the right side of the equation. It actually exists on the left side of the equation, so we'll have to flip the top equation. So let's go ahead and flip this one, and you can write flip if that works. So I'll go ahead and put water on the right side, on the left side now, plus 2 CO2, giving us C2H2 and 5/2 oxygen. The delta H now, anytime you flip an equation, you flip the sign. So delta H is now positive 1299.6 kilojoules. We can now cross this equation out. So it's going to get a bit messy, but we'll try to make sense of it here. So let's see, and again, the H2 will come from this third equation. H2 is already on the left side. We have one of them, so it looks like we won't have to do anything to the H2. So let's see whether we can find anything that cancels out. Well, we see that water is on the right side of the arrow here. It is on the left side of the arrow here. So water will actually cancel out. The same thing with CO2. If you find there are 2 CO2s on the right side of the arrow, there are 2 CO2s on the left side of the arrow, these two will cancel each other out. If you take a look at the oxygens, we have 5/2 oxygen on the right side of the arrow. We actually have a half an oxygen here and 2 oxygens here. That gives us 2.5 oxygens on the left, and 5/2 is the same thing as 2.5. So these will also cancel out. What you're left with then, that did not cancel out, are 2 carbon on the left side of the arrow, an H2 on the left side of the arrow, and a C2H2 on the right side of the arrow. Exactly what we want in our final answer. So then, in order to calculate the delta H for this reaction, we simply add up all of our delta H's. And go ahead and do that to give a final amount. Let me rewrite it here. So the delta H final will now be 1299.6 minus 787 minus 285.8 for a total value. So go ahead and take and try this on your calculator to get 1299.6 minus 787 minus 285.8. That gives us positive 226.8. And that is precisely our delta H value for our final equation. So you got 226.8 kilojoules. So this allows us to determine again the delta H of a reaction without doing an actual experiment, but using the delta H's of previous experimental results from these 3 reactions. And this is the power and the beauty of Hess's law. And a quick discussion of why this works. The reason Hess's law works is because it is something called a state function. Now in chemistry, a state function is a function whose properties depend only on the state of the system and not on the path in which the system came to that state. So a real-life example is this. Say if you wanted to travel from St. Louis to Chicago, and you can take many different paths from St. Louis to Chicago, but the difference in altitude will be the same. So no matter if you go west and go up to the mountains and come down to Chicago again, or if you go east and kind of drive around some plains, look at some fields, with some cows, in the end, what you'll find is that your altitude difference is exactly the same no matter how you got there. So it doesn't matter if we take 4 different reactions to get there or 1 or 2 different reactions to get there. The delta H is the difference between the heat of initial and the final condition. So the heat will be the same no matter how we get there. And we usually signify this with a capital letter. So if you recall, we talked about heat as being Q. This was heat for us previously in the chapter. And the reason we didn't use Q here is because Q is not a state function, but H is actually a state function. That's essentially why we defined a new quantity. That's why we differentiated between heat and delta H. And that should do it for lesson 4 of chapter 5.